Welcome on online lecture series in wireless mobile communication. Today we are having a topic outdoor propagation model. In previous lecture, we already seen the outdoor propagation model, Longley-Rice model and OKUMURA model. So continuation in OKUMURA model. Uh, Today we having some more specific topic to add a OKUMURA model. So there are so many students who are not seen the previous lectures. Now I am taking the first of a brief recap for this topic. Then we are taking the outdoor propagation model. So radio propagation model having a definition, the radio propagation is nothing but it is an empirical mathematical formulation, and it having the certain function of characterization uh, for frequency and distance and other conditions. The other condition is a specific condition which lies in between transmitter or receiver in a free space path, that is environmental scatters which are in the form of either land, or you can say tall buildings, mountains, rivers, bus, trees, etcs. So why we are going to formulate propagation model? Because the model help in predicting the behavior of the radio propagation under in this different constraint. And we go for to predict the path loss prediction determines the effective coverage area of the transmitter. To understand how the radio waves are effective by three types of phenomena. First is reflection, refraction, and diffraction. In reflection, when the waves bounce from the uh, any surface back towards the source, and in refractions, waves are defective when they are go through a substance like buildings, malls, or other things. They generally change the angle of its general directions. Diffraction is taking place when there is a sharp cut is geometric view, or you can say shadow is present when the wave goes through the small hole and has a flattered out the geometric shadow of this slit. So one can hear the sound corner because of the diffraction of the sound waves. Absorption is taking place when the light is propagating in this free space uh, medium, and it will be absorbed by like waters and other things. So the amplitude of the original wave is shorter than as compared to whatever the sending waves are sending from the transmitter towards the receiver. So this is called the attenuation. So attenuate means the waves are actually distorted during the propagation. They are not exactly fell on the receiver side. Polarizations, it is the property of certain types of waves that describe the orientation of your oscillations. So it in our wireless mobile communications, polarization is taking place 0 to 180 degrees, and after that there is no polarization is taking place. Only this 180-degree polarization is having the different types of the phases. So the this multiple components of waves are having the similar as in a count in you can say in amplitudes, but it is differ from its phase. So electromagnetic waves such as light, gravitational waves exhibits the your polarizations. Another phenomena is the scattering. Scattering is the some form of radiation such as light, sounds are forced to deviate from the start trajectory by one or more localized non-uniformity in the medium. Therefore, they are passes and they are scattered in a free medium in all possible directions. It becomes important to understand the system operation to achieve the required signal intensity or the quality of the service. Now, continuation in the radio propagation model. We are now today our topic is outdoor propagation model. Outdoor propagation model is viewed in this pictures. uh, there are the two several transmitters are situated in this geographical views, and one is there is a antenna which is receiving your transmitted signals. So this free space zone is divided from surface of the earth towards to the uh, in up directions. It having the three layers of medium in atmospheric uh, field or regions. The first region, which is from Earth surface to taking the 16-kilometer distance in a atmosphere, that layer is known as tropospheric region, a layer from Earth's surface to around 50 to 400 kilometer. That region is known as ionization layer or regions. So the near to the Earth's surface is uh, tropospheric regions are scattered the transmitted waves. So the waves are strike in this region. The atmospheric molecules, atoms, yeah, ions are scattered this waves in a different uh, waves, or these waves are split in many one waves are split into the uh, multiple components of the wave signals, and they approaches towards your receiver end. We are believing if we you have seen in my previous lectures, the free space propagation is only due to line of sight like this directly send towards your near tower, and it is travel as straight path. When the path is not a straight and it's reflected, yeah, other phenomena is scattered, yeah, diffractions is taking place during the course of transmission and receiver. So the when the waves are reflected bounce like this, they are called the reflected waves, and this waves are also known as non line of sight, non LOS, in short form NLOS. So this is the non-nanosite reflected waves. This is the line of sight waves, that is nothing but LOS. This is the one type of NLOS due to diffraction phenomena. This is the multiple component split in the single component is split into the multiple signals components, and that is having the LOS suffix में L minus 1. This is L minus 1 started from the I. So such type of uh, radio waves propagation is called outdoor radio propagation. Now move towards our next slide. So the radio propagation model having the certain types of the characteristics. In the above diagram, we have seen the radio wave propagation encounter terrains, path, obstructions, atmospheric conditions. They cannot be modeled by a single mathematical formula to determine the exact loss. So, in this view, we are having the resultant of sum of all these multiple components, and we modeled into the different model to exist for different radio path loss, radio path under the different conditions. So the radio propagation model focus on determining the path loss by assumption of certain conditions and modeling the distribution of signals over different regions that allow to understand the coverage area of the transmitter. So development of the methodology, it is divided into certain things. One is the how we have model our this radio wave propagation. So the propagation model, if it really implemented, they implies that the empirical in nature. So they required a large collections of data. If the we are going to collect this large type of different signals data in a different locations, then it becomes more uh, accurate when we are going to find out the our predictions values. Generally, our this free space path is divided into hexagonals, and the smallest unit is the microcells. So they are divided into the similar smaller size of the microcells. So the microcells are generally large, providing the uh, providing a coverage range on the order of kilometers and used for outdoor communications. Several times we have seen that this empirical path loss model has been determined for macro cells. So different models are developed under a different conditions, and that is as follows. First of all, we already seen the indoor application. Now see the outdoor applications. The outdoor application is started from the ground wave propagation models, sky wave propagation model. So this propagation, sky wave propagation model can be viewed like if consider this is the our earth, and shown by this hatches line, and it is the earth is having a certain curvature, so it is in a curve form, and we put our transmitter, and here we put our receiver. So symbolically it is the transmitter, and this is the receiver. If waves are sent and they goes to straight and received by the receiver, then such type of transmission is known as line of sight. But in practically our earth is having the curvature, yani curve area, so we cannot say the line of sight are taking place when we are putting the transmitter and receiver and that particular geographical area. Certain types of the height of the antenna and the others factors are also influencing the transmission of your radio waves. So it is not easy to transmit easily to send your transmission towards your receiver. So this free regions having the others some specific environmental effect. That environmental effect also taking into the consideration when we are going to model the outdoor propagation model. This environmental effect are weather, air flow, raining, the like your dust particles, others human-made buildings, trees, malls, lamppost, uh, fog. This is the specific environmental, and that also play important role to in the form of obstructions to flow of the transmission. So whenever the weather is going to down, that means our transmission is also not properly taking place. And in this types of environmental effect also be taking into the our consideration. So the outdoor application is also having this types of the multiple components data. So when indoor plus environmental specific data are combined, they are becoming very huge collections of the data. That's why we are choosing the modeling the this radio propagation model in empirical way. So the skywave propagation model is the collection of ionization layer plus isotropic layers. These two layers, whenever they are combined, they are known as sky waves layers, and the propagation is taking place in these two layers are known as sky wave propagations model. When we are involved when we are involved in this specific environmental effect, so such type of model are attenuate your propagated signals. So having the name environmental attenuations model. When the transmission are in the form of line of sight, that is known as point to point propagation. So this point to point propagation is also known as phase to phase propagation. Point to point point to point propagation. And another thing is natural environmental effects also be taking in our outdoor modelings. This is called the terrain, natural gel, mountains, river, and balcony, sea. This is a terrain. So terrain is a by natural made things, and it is distributed in all earth surface over all uh, places unequally. So we need a other types of model, that is the city model. When the data is collected from different cities, then we are having in a field to know what is the our next predictions to help to design the specific type of the receivers. So the importance of your radio waves propagation is propagation studies eliminate gases work because they rely on the scientific methodology. By incorporating the propagation modeling as part of our analysis of process, and utilities can use the information to confidently employ the most efficient planning available to control the cost and performance. It is account for performance goal of the utilities growth expectations and unique land use the issues. The drawback of this radio propagation model is, since the propagation models are created using statistical methods, no single model will exactly fit in any particular applications. They can be only used in the parameter ranges include in the original measurement sets. So the environments classified as urban can have the different meaning in the different countries. So model need to acquire a good input data in the especially in the case of terrain models, and the empirical models are used with the great success, but the deterministic physical, or you can say the random physical models, are increasingly applied to improve your accuracy. Glossary means you having the certain meanings which are using in wireless mobile communication were in the terms of area types. So the area is divided into urban area, suburban area, and open. Urban areas are those area in wireless communication is build up city, or you can say the large town. They having the lot of population, a crowded area with the large number of buildings and two or more stories houses, and these tall buildings are human made buildings or in a large village closely interspread with the chain of houses and thickly grown tall trees. The such type of area is are say urban area. The suburban areas like villages or near to highway scattered with the trees and houses. The area which are near to close the industrial area having some obstacle near the your moving radio car, but still not very congested. So as compared to urban area, the population of in suburban area are having very less. The crowd are more in urban area, so it is very dense area. Most of the business time, the crowd will play a important role to sharing or distributing your information during the transmission and receiving. receiver. So the third types of area is known as open area. There is no obstacle like tall trees or buildings, your concretes, jungles. They are actually not built in this open area. So the no obstacle like tall trees or buildings in the propagation path. So the plot of this length, which is cleared of anything uh, around 300 to 400 meter ahead, such as instant, yeah, is, or you say farmland or rice fields. This is the open fields. Another thing is in glossary is the antenna gain. It is related to directly to the intensity of your antenna in a given direction to the intensity that would be produced by hypothetical ideal antenna that actually radiate equally in all directions. So when the signals are propagated in all directions, such type of antennas is called isotropically antenna, and they having the no loss. So they having the unique gain, that is G of transmitter and G of receiver is equal to 1. From the formula, gain is equal to 4 pi radiated in intensity to the antenna input power. So you can say uh, this is given by your formula, like you can say 4 pi of d square divided by power of transmitter antenna. It is only valid in isotropic. So that is power density. It is the power density. And that is given by W transmitted power to the area. So the transmitted power area is 4 pi r square. Here the distances in separation. So it is the 4 pi of d. That area in a circular form. So and the it is the surface area of your transmission, and the size of cells is three types: macro cells, micro cells, and pico cells. So macro cells of the networks sizes are as compared to micro is large. It having the values of around 1 to 20 kilometers macro cellular network, and the size of micro cell in cellular network having the cell size of 400 meters to 2 kilometers, and the pico smaller cells, the like pico cellular net means you having the this hot spot, and to connect the another device with the help of this hotspot, and after that they're having the some certain types of chain. Such type of cellular net is called picocellular nets, or either it is connected by hotspot or Bluetooth. So such network are having a very small range. That range is around 4 to 200 meters only. In a case of Bluetooth, it is having the only 10 meters. The field strength, it is the magnitude of the received electromagnetic field which will be excite a receiving antenna and thereby induce a voltage at a specific frequency to provide an input signal to your radio receiver for the application such as cellular broadcasting and the variety of the other radio related applications. So another glossary is the path loss. It is the reduction in the power density. It is the reduction in the power density path loss. It is reduction in power density attenuation of electromagnetic waves as to propagate through space, that is given by L, and it is calculated in dB. So taking the logarithmic, so tan n log d plus c, where n is the path loss exponent, d is the separation distance between the transmitter and receiver, c is the constant that account for the system losses. So outdoor propagation model, uh, propagation over a irregular terrain. So whenever the irregular terrain, natural specific environmental effects are taking place, then we are producing the outdoor propagation model. In this propagation model, the predicting signal strength is very widely, their capacity, approach, and accuracy. As you know, Longley-Rice model, which is also known as irregular drain model. So it is also called ITS. In this model, the frequency ranges is 40 megahertz to 100 gigahertz. It's having the two versions. One is for the point to point using the terrain profile, and when we are having the version in the field of area mode, then it estimate the path specific parameters. Our OKUMURA models are having the specific set of curves which is giving the medium attenuation related to the free space in the urban and over a quasi smooth terrain. So the L50 dB is the 50th percentile, that is the median value of propagation path loss between transmitter and receiver expressed in dB. LF is the function, is the free space propagation loss in dB. AMU of F and D parameters. So AMU-FD is the medium attenuations relative to free space additional losses in dB due to propagation in urban environment when the transmitter or receiver at reference heights. And this G of H of TE, it is the base station antenna height gain factor in dB. H of GHRE, it is the mobile antenna height gain factor. It is also calculated in dB. And G area, the gain due to type of terrain in dB. So this is the figure which is actually taken from the your Rappaport book, and it is having the three axes. One is x-axis, that is the frequency uh, calculated in F megahertz. It having the two vertical axes. This is the first axis, which is 10, 20, 30, 40, 50, 60, and 70 scale, and it is the medium attenuation AMU F of D dV, and inside this vertical axis is the separation distance in kilometer, and it having the scale 1, 2, 5, 10, 20, 30, 40, 50, 60, 70, 80, or 100, and it goes up to frequency ranges. When it is 1 kilometer, and the frequencies is started from 10, 70, 100, 200, 300, 500, 700, 1000, 2000, and 3000. So in a 1 kilometer, it is about goes to 3000 megahertz. When your distances is 2 kilometer, the frequencies ranges to 100 to 3000 uh, megahertz. So when we drop the slope on this line, we getting the actual you, actual value of your GH of T, GH of RE, and GH of RE. So a OKUMURA path loss model now another graph is in between the frequency and the correlation factor GA area in dV. It is divided into the three area. One is open area, second is quasi open area, and third is suburban area. And the scaling is frequency in megahertz: 100 megahertz, 200, 300, 500, 700, 1000, 2000, and 3000 megahertz. And in y-axis, correlation factor is started from 0, 5, 10, 15, 20, 25, 30, 35. And here you can see the same scale in urban area. H of T is 200 meter is given, and H of R, that is the height of the receiver, is 3 meter. So basic medium attenuation AMU, if we taking this graph, so it is the model additional propagation losses due to signal propagation with this referred conditions when terrestrial urban environmental over a quasi smooth terrain, and when the base station effective antenna height H of T is 200 meter and mobile antenna height is R equal to 3 meter. And another thing is the if the actual height of transmitter receiver or the propagation area type differ from those reference, then we having the appropriate correction needed to be added. So Likewise, uh, we having the formula OKUMURA profile L50 dV is equal LF plus AMU F comma D minus G H of effective antenna height gain factor of transmitter and effective gain factor of antenna height of receiver and G area. This is the our OKUMURA equation number 1, and this is the OKUMURA path loss equation. OKUMURA path loss H of TE is equal to 20 log of H of RE to 200. The range is 1000 meter to 30 meter. And for effective height of gain antenna of receiver, factor is given by H of GH of RE is equal to it having the two values at 10 log H of RE divided by 3 and at 20 log H of effective height antenna gain factor is 20 log H of RE divided by 3. H of RE is less than is equal to 3 meter 10 meter to 3 meter. H of RE so you can see this OKUMURA model is wholly based on the measured data, and there is no provision for the analytical explanations. So a OKUMURA model is considered to be among the simplest and best in terms of accuracy in path loss prediction, and it is very practical and has become a standard for system planning in modern land mobile radio systems in Japan. And there is the one disadvantages over a OKUMURA model is the slow response to rapid changes in terrains. Therefore, the model is good in only in urban and suburban area, but not good as in rural area. So, see the one problem on this topic. Find the median median path loss using OKUMURA OKUMURA's OKUMURA OKUMURA model for D is equal to 50 kilometer and height of transmitter 100 meter, height of receiver 10 meter in a suburban 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 environment if the base station if the base station base station transmitter radiates as RP of 1 kilobyte at a carrier frequency of 900 900 megahertz. Find ERP dBm and the power at the receiver where where, where, where gain at receiving antenna receiving antenna in antenna is 10 TV. So first of all, let us what is given that distance this this separation distance is 50 kilometer. 50 kilometer height of given effective height of transmitter is 100 meter. Effective height of receiver 10 meter. ERP ERP is equal 1 kilowatt. Frequency is equal 900 megahertz and gain of receiving antenna G of R is 10 dB. This data is given in the question. Now write up the equation of a Kurma path loss L50 dB is equal to LF plus AMU of F comma D minus G of effective height of the transmitter gain factor, effective height of the receiver gain factor, and area GERA. So the first of all, our requirement is to calculate LF free space path loss. That is LF. Free space space path loss LF is equal to minus 10 log lambda square to the 4 pi whole square d cos square. Putting the values of all these parameters, where lambda is C upon F, that is 3 into 10 की power 8, frequency is 900 into 10 की power 6. So it is 3 by 9. Ten 900 into 10 की power 6 की power 2 पाई की वैल्यू 3.14 का होल स्क्वायर separation distance is 50 into 1000 10 की power 3 and this is around 125.5 dB. The OKUMURA from the OKUMURA curve curves AMU at 900 megahertz 50. How you calculate this value? Frequency is 900 and range is 15. First of all, draw the perpendicular on a frequency fmh, then draw the perpendicular on a median. It is cutting here. Value is 43. So AMU is at 900 megahertz to 15 kilometer. Separation distance between transmitter and receiver is 43 dB. So value is 43 dB from the OKUMURA graph. अच्छा भैया, अब calculate the G area From G area is 9 dB under the frequency of 900 megahertz. So from the graph we have calculated the values of G area from the y-axis. We have first of draw the perpendicular on suburban area curve, and from here to drop another perpendicular on the scale of G area dV. So it is cut air 9, so value is 9 dB. Now put the values of this A 9 dB. So using the equation G H of T E is equal to consider height of transmitted and effective antenna is 100 meter. So 100 meter is lies in this range. So we are taking this equation 20 log h of t divided by 200. 20 log h of two, 20 log h of t is 100 meter. H of t is 100 divided by 200. 0 0 कट गया, 0 आया 0.5. minus 6 dB. G height R is 10 meter. So 10 meter is lies in this equation. In this equation, it is less than 3 meter. It is 10 to this. So we are taking this equation 20 log h of RE divided by 3. Until 10 by 3 is equal to 10.46. So using equation for the total mean path loss. LFAMU F comma D minus gain factor at antenna height transmitter minus gain of antenna height receiver gain of area. Put all the calculated values in this formula. For free space we are calculating 125.5 dB on 25.5 plus AMU is 43 dB and DVM gain of -6. It is 6 minus 6 dB minus 10.46 dB and last minus 9. It is coming 155.04 dB. Therefore, median is received power at distance ERP dVm minus L50 dVm plus gain of receiver in dV. This is unknown. Now calculate EIRP. EIRP is given in dVm, conversion in dV at 10 log EIRP milliwatt to 1 milliwatt. That is 10 log of ERP ERP is this 1 kilowatt. Is 10 log 10 की power minus 3 ऊपर जाएगा positive, it become positive, so you can write 10 की power 6, so that is 10 into 6 log 10, so it around 60 dB. So receive power, we have ERP 50 dB plus gain of ERP is 60 dBm or L-50 is 150.04 dB. 155.4 D plus DR is 10 dB. So value is minus 85.4 dBm. The drawback of a OKUMURA model is based on measured data. There is no analytical explanations. In certain cases, causes can be X. So, thank you very much.